My name is Robert Uri. I am with EDSL, as Jack so aptly described, and I'm here with my colleague, Michael Salford. We are going to talk about integrating building energy modeling through a standard called the ASHRAE 209 standard. So we'll talk a little bit about what the 209 standard is, and then hopefully demonstrate how tasks can be used to satisfy that standard. Then we'll go through just a little bit about tasks, and hopefully leave plenty of time for Q&A after. So thanks for joining. So a little bit about ASHRAE. If we have many engineers in the crowd, I'm sure you're no stranger to ASHRAE, but just for those who aren't familiar or might not know a whole lot about ASHRAE, ASHRAE is a 125-year-old organization that I don't think it's an acronym anymore, but it used to stand for, very long, hold your breath, the American Society of Heating, Refrigerating, and Air Conditioning Engineers. Again, 125 years, their stated mission is to serve humanity through advancing heating, ventilation, air conditioning, refrigeration, and allied fields, and their ultimate vision is a healthy and sustainable built environment. So when I was growing up, my father was a mechanical engineer, and I remember always getting the issues of the ASHRAE journal, but I didn't really know what it meant. Now, of course, I know a lot about what it means. I used to think it was just guidelines for how to make ductwork and so forth, but not so much anymore. I think one of the things that ASHRAE is really known for is their proliferation and authorship, community-based authorship of standards. They write a number of things in addition to the standards, one of which being the ASHRAE Fundamentals Guide, which is essentially HVAC 101 in terms of building physics and how buildings operate. When I was going through architecture school, I had a gigantically thick book called Mechanical and Electrical Equipment for Buildings. The ASHRAE Fundamental is effectively the definitive guide for the industry in how HVAC systems work and how you approach design and the building physics behind them all. So fundamentals notwithstanding, I just highlighted a few of the ASHRAE standards that were particularly pertinent for us. Again, the standards that they author are wide-ranging. They cover everything from the classification and safety of different types of building refrigerants. They develop data standards for data protocols for how building automation systems can communicate with each other. But some of these are the ones that are most pertinent to what we talk about. So ASHRAE 55, thermal conditions for occupancy, 62.1, setting acceptable indoor air quality, the amount of ventilation that's required for that. One that we like particularly, 189.1, criteria for high performance green buildings. 90.1, which we'll be touching on a little bit later, are energy standards for buildings. Actually, 90.1 has been adopted into some LEED requirements, which we'll touch on a little bit later. And then probably the one that is nearest and dearest to our heart on a day-to-day basis is 140-1, which tests the validity of the results from building energy simulation software. So that's basically every time that we have a release of tasks, we have to run it through the certification process to make sure that it meets these guidelines. And so do all the other software manufacturers. So it's a way to keep us all honest. So thank you, ASHRAE, for that. Today, however, we are talking about ASHRAE 209. So the 209 standard is, as you can see, the energy simulation aided design for buildings, except low-rise residential buildings. You can see ASHRAE is not known for their brevity in the titles, but really that's what it does. The idea behind ASHRAE 209 is to find a way to better integrate building energy modeling throughout the design, construction, and occupancy life cycle of a building. So too often, I'm sure that you've all experienced this, too often somebody comes to you or comes to you may perhaps have to go to an engineer at the end of design development or the beginning of construction documents and say, hey, can we run an energy analysis on this building? And of course, you've either said or have been told, why didn't you come to me sooner? Because then we could have made more effective recommendations. So the idea here was a standard was written around the idea of trying to figure out what types of building energy analysis and what types of building energy simulation would be applicable at what phases in the design cycle. So some of you may be aware of the Architect's Guide to Building Performance published by the AIA. It used to be called the Energy Modeling Design Guide, but there was a new edition out this year and they've changed the name. We were proud to have participated in the review process of that. But in there, there's a graphic, which is hard to read, admittedly, that does its best to map certain aspects of simulation, which is up in the yellow, across the design and occupancy cycle of a building, which are the top headers all the way at the very top that go from left to right. But then if you take a look down bottom, everything that's in blue, this is actually, and you might, if you can read the fine print, great. If you can't, that's okay. But next to the title, Whole Building Energy Simulation, they actually reference the ASHRAE 209 standard. So this graph basically does its best in a nice visual way, thanks to the AIA, to map certain aspects of building energy modeling to different points throughout the design lifecycle. So I found this a little difficult to read, so we made a simpler version of this. Hopefully we can just go through it. So as you can see, the column on the left takes you down through the design cycles. And then sort of the lighter shade blue are aspects that we'll be talking about as it relates to tasks and how you can accomplish each of those in our support tasks. So we've got, for conceptual design, or RFP, RFQ, we've got something called simple box modeling, and then conceptual design modeling. Michael will be happy to go through those. And then in schematic design, load reduction modeling, which is basically where you're trying to find ways and design strategies to reduce the heating or cooling loads or energy loads on the building itself. So if you can prevent the energy from being used in the first place. And then also some very schematic system selections to try to figure out how you might develop your design around different active and passive strategies for the building itself. Then in design development, much like the architectural cycle, you begin to do the refinement of that design. You begin to sharpen the pencil a little bit, provide a little bit more data, go through some iterations, and then you begin to integrate your systems and optimize, let's say, the sort of the template-based systems to the specific building uses. In construction documents, 209 standard calls out for simulation-aided value engineering. So inevitably, someone's going to think something costs too much money and is going to ask to see if substitutions can be made. So there's a section in the standard that covers what sort of energy modeling might be suitable for the value engineering process. Then in construction, you're beginning to assess the as-designed performance, effectively beginning the calibration of your building energy model, and then how to handle change orders, much in the same way that you would do simulation-aided value engineering in the CD phase. And then in post-occupancy, how you can calibrate a model, how you can utilize energy modeling through the building's occupancy life cycle, and then also how it can feed back into future improvements. So that's a very quick 50,000-foot view of the types of energy analysis that are used throughout the design and occupancy life cycle. And I'm going to hand it over to my colleague, Michael, at this moment, so he can begin to talk about the first phase, conceptual design, and what's required within it. So thank you, Michael.
Thank you, Rob. Hey everyone, thanks again for joining us. So I'm going to run through some of those modeling cycles at still a fairly high level, and how they pertain to different types of analysis and levels of fidelity within your model. So the first one mentioned was simple box modeling. So this could be, even without a box, you could do analysis just on the site location and the weather. But if you do have a box, then you're analyzing things like exposures for solar and daylight, and basically super simple load calculations based on very simple models like the one shown here, where you may have walls. These look like fully glazed walls in the top left-hand corner, but they could be percentage building elements, meaning that a percentage of the wall is made out of glass and a certain percentage is made out of an opaque surface, and you can just play around with changing percentages until you work out window to wall ratios that you would like to analyze further, and then you can start doing like strip windows for analysis. And it's very easy to do this type of analysis in tasks, but what we found in practice is lots of this analysis has already happened before people are coming to our software in tools based in Energy Plus. So there are lots of plugins for Grasshopper that use Energy Plus in the background, and there are other ones that use it also pertaining to Grasshopper. And basically, the data behind those models can be read into tasks, which has a couple of benefits. One is that you can bring it into an environment that can go through all the way through the rest of the life cycle of the building. The other part is you can just review the assumptions made in those tools and tweak them as granular as you need to as you progress, getting more and more refined data for your model. And then once you've done that, TAS also allows you to export the information back to Energy Plus, so you could hand it back off to your fellow architect colleague who's using a Grasshopper tool or something, versus maybe even an engineer who's using Energy Plus that you're working with. could do that. And if you are the engineer, then you have a way of reading Energy Plus data and writing Energy Plus data. So it just helps the communication back and forward with the BEM data. So it's kind of a BEM interoperability that can help with this early phase, early analysis bit, which also goes into the CD phases as well. So then basically building up into schematic conceptual design, where maybe you don't know the final shape of a building yet, but you know the space types you have to analyze, and you want to see what those exposures, how those exposures, different orientations perform with different considerations. So this is looking just at different sun angles for solar and sunlight exposure, and also daylighting analysis mixed in with natural ventilation. So we have daylight being analyzed for this particular array of windows that have been applied. That could be changed back and forward as you iterate between the daylighting and maybe impact of different window configurations, different operable windows, maybe having only the top row openable and things like that, just playing around with one room in a particular building, moving on from the one zone for a building in the simple box modeling type analysis. So once you get out of the conceptual design phase, and I'm skipping through that quite quick, but you would have several iterations going through different ways of analyzing the building, different aspects of it, single aspect, the whole building aspects. You may go into load reduction modeling, where you could look at, again, more refined building forms. This is one story building. All the zones being analyzed, and in this case, just for the temperature as it pertains to responding to the natural ventilation. So you see the wind direction changing with the green arrows, and response of all the apertures with the blue arrows of the cold airs going in, and the red arrows with the warm airs coming out for the building through a course of a typical day. So this type of analysis can be performed, again, a simple level of detail, building up to more levels of detail in the same type of thing, where you're trying to look at load reduction. So here we're looking at if you're naturally ventilating a building and you're looking at the dry bulb temperature, which is the temperature in the air, the left graph shows that all the temperatures are very comfortable and all green, all good. However, including the solar gain, mean radiant temperatures effect on the overall zone temperatures, you can see from the right-hand side that mean radiant temperature calculating the operative temperature in the middle, which is basically what the occupants are more likely to feel. And that highlights a need for potential shading on the south facade. So this is just, again, just to show maybe natural ventilation schemes are working but one level of detail, but then when we're building a bit more, we find out if we're not considering shading for naturally ventilated spaces, we're still maybe producing not comfortable spaces. And again, all this is just doing passive analysis at schematic design. And when you've defined shading schemes for your building that work for solar natural ventilation, you then consider the internal light implications of that. So there's some ray tracing simulations that are possible in TAS to do these interior shadow simulations. Building up to larger projects, but maybe just a typical floor, changing glass types between for the facade, impacting on the lower right hand side. You can basically see the solar gain through the year hourly, and you can see one glass is controlling the solar very much, the other one's letting a ton in, and that impact is, yes, the cooling goes up in the summer, the heating goes down in the winter, and then that's the central one is the sensible load. So heating's above the zero, the zeros here, and cooling is below zero. You can see there's a much larger cooling amount from the higher solar gain. However, with natural ventilation being allowed to use in the occupied apartments, you're also increasing the amount of hours where zero heating or cooling is needed in the periods before and after summer. This particular project being in Toronto, it was cold. It was a cold climate anyway, and the system for cooling efficiencies were much better than the heating, so it can balance out. But again, this is, again, as you're working through the design options for a project, analyzing how you can reduce those loads. Another thing after doing that is things like, once you've done those early concept daylighting model analysis, being able to integrate that into lighting controls. So doing daylight dimming. So you can see here, this is the interior lighting load. You can see every week this office, because the weekends are the gaps. And you can see how that dips down for all the zones in the building at different levels through the year with that daylighting control. And it saves, basically this block would be filled in without the dimming control. And that reduces the internal heat in the space, which allows then again, some more hours where you're going to hit 0 sensible load, so no heating or cooling required, as shown in this little area here, zoomed in. The next part in this modeling cycle focuses on basically templatized HVAC system selection. So you're not really drilling down into all the setup of those. You're using typical setups, but you're maybe changing out different types of systems to analyze. So there's a bunch of templates and tasks that you can pick from. They're shown on the left, and all of the baselines systems from 90.1. The idea is you just pick the type of system, apply it to a certain subset of thermal zones in your model, and then run it and see how it performs, and then compare that to other systems analyzed. As we move to the next cycle in design development, design refinement, integration, and optimization. So here, there's more of a solid idea of the geometry and the shape of the building, but you're really just refining all the parts and pieces that make up the geometry further when you've taken those smaller concept models and applying them at a larger scale in the model. So here we have an actual whole building, just looking at sun and shading for the whole scheme, focusing on the south exposure in these two videos. As you can see, the sun position shot on the left and the shadows shown on the right for a fixed time and day. Here moving to show one floor plan from that building being analyzed, instead of just a couple of rooms being analyzed for daylight, moving up to a climate-based daylight modeling approach where multiple hours through the year are analyzed. We do analyze the whole year when we do CBDM analysis, and in this case we even reduce the grid spacing to 10 centimeters or a third of a foot square, so much less than is needed for LEED, just to get a super granular grid to see what was going on, and also to test the software out for its performance. But again, this is just so you can review that in the context of an entire floor for the project. Annual installation, so looking at the solar gains on the whole building form, in this case just selecting those dorm rooms, the same ones that were analyzed for daylighting, picking a subset of the spaces to test how the shape of the building is impacted by solar, and then seeing the convex piece, the pointing towards the sun, how that's getting hit. And you can basically in-task mouse over any of these surfaces and get the data reported back for the actual annual insolation reported for that surface. So it's interrogatable data. Looking at sunlight availability, the flip side of that, showing the penalty for being in the recessed corners, the concave parts of this building as it looks south, and the impact on the sun availability for those spaces. So you see 47% if you can just make that out on the left, whereas you have 80% on the most south-facing part exposed. And again, taking natural ventilation as a concept of analysis, applying it to the whole model could be useful, but also before doing that, maybe picking a subset of rooms to analyze just different orientations for natural ventilation to check how it works different times of day, different times of year. So this is looking at a day in April, 9 a.m. or 1 p.m. So in the morning, it actually still maintains comfortable temperatures for these different orientations. But by noon, when the sun's really up, the high exposure bit with solar and annual insolation was very high, is basically is too hot. And there's no air conditioning in these rooms in this particular building that was finished. They'd had to put HVAC units on it if the students in this building were still there by 1 o'clock, if people recognize it. After doing that, just analyzing things, optimizing. So when you don't really find, you can't find a clear solution for many things in building simulation because lots of variables overlap and result in different outcomes. So optimization can help when you want to basically take a few things like shading and daylighting, calculate maximizing daylight availability and minimizing peak cooling load. And this is basically running a series of options. You see that the gray bar, the gray shaded area is the result of this analysis, and the idea is to minimize that down to as a small impact as possible. And you can see basically it starts changing variably through the first half of the analysis, and then it kind of settles down into a particular result space. And there's a series of algorithms available in our optimization piece that came from LBNL's GenOpt tool that we basically created a C# scripting interface for in tasks that allows you to run these generic optimization and parametric analysis types with. So we looked earlier at that dry bulb versus mean radiant temperature and operative temperature with the passive side of things, with natural ventilation, solar, and potentially solar shading. You can also analyze active radiant options in TAS. So here's modeling of an underfloor heating and cooling system. And once you do this, you could spot check, just like the NAT vent, spot check a few rooms before applying it to the whole building to see how that performs as you're doing the design environment to just check things. So here we could check things like the surface temperature of the floor, as well as the air temperature. So floor surface temperature is labeled up here, the air temperature dry bulb here, and the operative temperature of what the occupant feels down here. So you can see the underfloor cooling is actually bringing the temperature felt by the occupants much lower, and then potentially using less energy to do so. This goes into the murky area of simulation aided value engineering, where something costs too much. So we're going to make some changes. But the 209 book, basically, the simplified version is it asks you to assess the implications of those changes through modeling. So say you inspect a particular mechanical system for a building, and it was being considered too expensive, so you could change it out. So here, the generic systems were analyzed, passive and active beam. Maybe one of the systems came up too expensive, but by maybe picking something more specific and running that analysis, you could see the impact was going to be more cost effective in the upfront cost of the system, but also maybe saving some energy overall. And again, so this is comparing those template systems with more refined detail as we get into the completed project design documentation. As you get into construction as design performance, the piece I'm going to highlight here is actually to do with the 9.1, as Bob alluded to earlier. I'm going to talk about this for a little bit. ASHRAE 9.1 Appendix G is a compliance path for the standard now from 2016 onwards, and has always been part of LEED as well. And we've always, since 2007, we've had a studio that's been added to over the years to automate the process. Basically, this means that we take the proposed as design model files and generate all the baselines. That can be the geometry files, the simulation files, and the HVAC files to do all the simulations for you. So you end up with all the model data and the average baseline against the proposed results all created for you. And then moving on from that into the post-occupancy and model calibration phase for the as-built. So reassessing what the commissioned building space ended up being. If there are any change orders not assessed or value engineered, this is where you can go back and reassess the as-built performance. This example I have to run through goes a little beyond what's needed in the standard because it was a research project, which basically meant that it got access to more data than you would ever typically get on a project. Such as the ability to not just use a more up-to-date weather file for the location, but actually install a weather station on the roof of the project and record the weather data for 2 years and use that to drive the analysis. Having manufacturer's equipment data available for all of the equipment installed and putting that into the model, getting sub-metering data for the spaces, full access to the utility bills, and even the BAS system, BMS systems, and all the data from sensors as the building was under operation, to basically create a calibrated energy model to do the post-occupancy performance gap analysis. So through this 2-year project, the last year is plotted here with the blue charts being the bill sent to the client, and the red being the calculated energy consumption calculated energy cost for running the building from TAS in red. There's some discrepancies. At the start, there were very many more due to lots of different reasons I haven't time got to go into, and this was a very good learning experience for us to work out how to do this calibration process very thoroughly, resulting in very, very close comparisons between the model and the reality. And it is always still a model. The good thing was that when we got down to some things that should respond pretty closely, not just at the monthly or annual level, at the hourly level, this is a sensor on one particular pipe in the mechanical room. And this is the same pipe in our HVAC schematic reported for the same period from the summer through to the winter. And you can see the shapes very closely matched. Ours is obviously a bit tidier than the actual sensor that's a lot more, real and messier. But we're very pleased that kind of helped us to provide some more empirical validation for the software, along with showing the value of post-occupancy performance. there was a series of measures implemented on this project that led to many savings. It was 150,000, I believe, a year annually saved on the project every year afterwards. And also part of that was actually just improving comfort of the 4 stories of office spaces that make up the top of the building with regards to humidity controls in the space. Another part of post-occupancy goes into equipment replacement and feasibility for retrofits. So in New York City, there's Local Law 97, which is going to just start having people to report their CO2 emissions. So there'll be many more of these projects popping up. This is just an example of taking one example building with measured data, creating a calibrated model to that, not as much detail as the past example. So it's just it's calibrated as much as we can with the data available, and then basically making changes to the mechanical system, updating that, knowing the upfront cost to make that change, and trying to see what the predicted savings could be for that new system to see if it's worthwhile to do, to get them on track for where they need to go for the law as it progresses through the next 10 or 15 years. Okay, so that was a brief bit about some of the cycles, some of the levels of detail in the cycles, and different types of analysis that you can do. Definitely not exhaustive, but I want to get into a little bit about TAST itself with some of the time we have. So what does it do? All the things that we've shown previously in the slides: whole building simulation, daylighting, natural ventilation, load calculations, HVAC sizing, and those sub 4 categories all fit into whole building simulation as well. What is it used for? Anything from design, analysis, code compliance, retrofit, and post-occupancy performance. So the full spectrum of the building's life cycle. TAST can be used to meet building simulation for those phases. So how is TAST constructed? This is the typical workflow in TAST. You have a 3D model application that allows geometry creation and daylighting analysis to be performed. So all of the daylighting graphics shown previously came from our 3D modeling application. That creates, that also does shading calculations, which can be distributed among multiple cores and multiple machines. So you can basically create a little like swarm of machines to do shading calculations to speed that up. The building simulator allows you to put all the rest of the building input information, occupancy profiles, the lighting controls, aperture types for natural ventilation, all the passive simulation and shading options get put into here. You basically simulate the building loads, and then that goes into the results viewer where you get to review that data in a lightweight results viewer program, which in turn feeds into the HVAC program where you get to use those template HVAC schematics, or even customize your own and build up as it's component based. You can build up schematics as for whatever you like on the air side and the water side, or refrigerants, VRF, and customize that as needed to do the HVAC whole building simulation to calculate the overall energy, EUIs, cost, and CO2 emissions for the building. So 3D modeler, you can draw or import geometry. Has import and merge functionality with BIM, so you can import a file once and then import a second file that's been updated and retain changes that you've made, but also update any additions that have happened. And there's ways to import BIM files as well. The building simulator takes the weather data for the location, constructions made up of, so what things are made up of. So here, just selecting one particular construction in the building, seeing where it's applied in the model, and then if you were to expand the little option, you'd be able to see all the material layers in that construction. Activities, so defining how many people are in an office space versus how many people are in a corridor, and again, these are the activities that are set up in the building simulation. And when you select those, you can also see where they've been applied in the model at the same time. TAST systems allows you to build up schematics for the plant room and the airside by component, or using those templates. So again, here's like a template fan coil system. It has live data that you can see on the schematic, as well as psychometric chart data. And there's data behind every single component. Every pipe duct has all the 8,760 values for all the variables that it stores available. And all these parts and pieces can be saved and reused in other projects into a library of things, as well as creating new fuel sources. We have a bunch of templates in there as well for those. You can create new fuel sources with new CO2 emissions factors and all the data necessary to define the tariff situation for the project. So flexible workflows with TAS. TAS is a standalone application that, as you go through that typical workflow, can meet the needs of most projects. But it's always not the whole. It's not the whole part of anyone's story. There's always something that goes on before and something that goes on afterwards. There's lots of ways getting data in and out, whether that's from just tracing CAD files to create the geometry, importing GBXML from Revit or ArchiCAD or any other GBXML authoring tool. There's ways into TAS, and then ways out. Always get Excel data in or out of TAS, video animations, images, customize and template reports. And we also have a BEM interoperability link with Energy Plus. You can see Energy Plus data going in and out. And we also take eQuest data in as well. So within interoperability, I touched on it at the start. It does allow the ability to read and write Energy Plus data from TAS, which can help communication gaps across teams. And also just exploring options within TAS and an environment set up to be able to get into whatever level of fidelity of information you want to get to, and then be able to create the IDF file and pass that back, whether it's the architect communicating with the engineer or the other way around. So TAS, we do love Excel, so there's ways to not only to copy and paste data to and from Excel, which you'd expect, but you can drive TAS with Excel macros, which I'll touch on very shortly. The idea in TAS, though, is that behind every piece of data in the model, there's all the raw data is available to get out. You can graph it and configure this graph to show different subsets of the model, different variables. You can also project that onto the geometry to help basically explain the data that's in the project to different audiences, and also to graphically review the information yourself. So you can quickly check what's going on with the building for different types of things, whether it's like the air movement gain between spaces, or if it's daylight or whatever. It's all in tabular, graphical, or 3D format. So it is extensible, as I mentioned. So with Excel, you can write VBA scripts to automate either the creation of files, modification of files, simulation, or extracting results. And you can do the same thing with VB.NET and C#, with C# being used in TAS GenOpt for the optimization and parametric analysis. So we did touch on this earlier, we saw a little video. This is just saying that the data is also behind all those options too. So you have all the options simulated on the left, 23 simulations in 7 minutes, but you get all the input parameters and all the output parameters that are specified in the script get exported too. TAS is approximately 30 times faster than Energy Plus. There's a lot of productivity savings for doing iterations on models by moving into TAS. It's multi-core enabled for all building simulation, and multi-machine, as I mentioned, for the shading calculations and for climate-based daylight modeling. So you can link together not only multiple cores on one machine, but multiple cores across multiple machines for even increased speed when you need to crank something up overnight to finish. Okay, and moving to the last little bit here with, we do have a new release of TAS that's just come out, TAS 9.5. This represents a big move forward in technology as it has migrated to a full 64-bit application, which has basically produced a bunch of benefits, such as the daylighting example I showed for client-based data modeling for an entire floor. That model, I said, with a grid space of 1/3 of a foot for an entire floor, took about 17 hours overnight. Perhaps daylighting models for 1 or 2 zones may take just that long with a larger grid space and current tools. Whereas with the 64-bit version, we're now not limited in the memory for the amount of spaces you can analyze at the same time. And so with chained machines, we could potentially have run the whole building at the small grid spacing overnight. So again, if you're thinking about just doing single zone analysis, you can do those in seconds to minutes, not minutes, hours, and potentially days as in other tools. Expanded and flexible licensing options, including some network licensing options now. A bunch of extra repetitive task automation processes developed for 90.1, load calcs, and lead. More interoperability workflow improvements that the Energy Plus import now creates a fully editable 3D geometry file. So you can edit the geometry, and some extra improvements to the UI of the product, which is continuing to improve on. So one of those key things in the test line improvements was the design day wizard to basically do ASHRAE design day load calculations automatically. You would basically it looks at the weather file, picks the nearest surrounding locations for you. You pick the weather location you want, and then it gives you all of the different options for the heating and cooling design days that you can choose to set up and then automatically run. Those can be run when you're doing the first initial load reduction analysis, and also later on when you're doing the full building HVAC analysis. The same design conditions can be used and reused. There's some improvements we made to the lead process, which includes updates to the 9.1 Studio for Appendix G, automating the baselines and all the efficiencies for that. But we've also extracted all of the baseline data, or most of the baseline data, into the minimum energy performance calculator spreadsheet that's required to submit to lead for review. So basically, once you get to the end of the Studio project and you've calculated the results, there's now a push button within Excel to extract the data into the spreadsheet to help. If you ever have to make iterations on your model, you don't have to then spend hours typing out all the information again into the lead spreadsheet before resubmitting it. It's just a push button to pull that data. And we're going to keep improving on the amount of data we pull out and into that spreadsheet. We also have automated daylight credit analysis and reports for lead as well. So there's another part that we're helping with productivity. So TAS is one tool that covers building simulation and sizing. It does help to minimize rework and data loss across applications and platforms, and provides better communication across teams and data exchange, so you don't have to recalculate things. There's not a communication gap, or it lessens the communication gap across those teams. And with all the productivity and automated tasks, it does produce time savings. Coupled with the fast speed of tasks, you can get much more QA and QC work done in the same time you would take to do one run. You could have done 7 and analyzed them all. One final note is it opened up with some of the CAD learning notes from Microsol. TAS is free to learn. There's a video-based online course that has all the core applications and chapters that take you through steps of learning how to do basically the fundamentals of how to use TAS, as well as a specific course to do 90.1 analysis. We also have workbook-based courses that you can download and follow along. If you want to watch videos, you have those. If you have the workbooks, you have those too. The online video course also has a bunch of example files. You can download the files at any point during the training. So you basically can get different levels, different ways into the training, and practice one extra piece instead of having to start from the start every single time. So that's really benefit, and we're going to keep adding to those videos online.